Hi, my name is Len Duda. I'm a member of the Albuquerque Astronomical Society, and I used to work at Sandia Labs. I retired about 4 years ago. I'm also a NASA Jet Propulsion Laboratory Solar System Ambassador. This is a program that the Jet Propulsion Lab started over 20 years ago. They have over 900 volunteers across the country giving presentations like you'll see today, plus being involved in other activities which are related to NASA solar system missions. And so today, what I'm going to show you are many images that have been returned by the Cassini spacecraft, which have been orbiting Saturn from about 2004 through 2017. It sent back lots and lots of images of Saturn and its moons. We're going to look at a few of Saturn's moons, the most prominent and maybe more interesting ones. We'll look at some images of Saturn and also some images of the rings. And so I hope that you enjoy this presentation. I'm going to go ahead and start my PowerPoint. Here we go. Cassini spacecraft at Saturn. As I said, I used to work at Sandia Labs. I'm also a NASA Solar System Ambassador. Okay, here we go. And here's a picture of the Cassini spacecraft. This was the one that had been orbiting Saturn until about September of 2017. It's a large spacecraft, about 20 feet high, and shown here pictorially. It has a large dish on top, which is used to communicate with the Earth. It has a collection of remote sensing instruments looking at the moons and Saturn and Titan in multiple wavelengths of light, as well as a spectrometer. Another kind of important feature is this radar bay. It was used to image the surface of Titan. You'll see why that's important. On the back, you'll see here partially is the Huygens Titan probe. This was a probe that was designed and built by the European Space Agency. It was launched from the Cassini spacecraft about 6 months after Cassini went into orbit around Saturn, and it entered the atmosphere of Titan and did scientific measurements of the atmosphere of Titan, as well as images of the ground as well. And we'll show a couple of images of that. Down on the bottom, the power source for the Cassini spacecraft are three RTGs, radioisotope thermoelectric generators. These use the decay of a radioisotope to produce electricity. When Cassini started out, those three RTGs were able to produce about 885 watts of power. At the end of the mission, they were producing 633 watts of power. And here's a picture of Saturn and its moons. To me, Saturn is really kind of interesting because it has a wide variety of moons. 53 of them are named. It actually has 82 moons. It actually leads the solar system. Back in 2019, scientists added about 20 more moons to Saturn, so it leads Jupiter by about 3 moons or so. But what makes Saturn really interesting is that it has an assortment of moons which are fairly large. 10 moons have diameters greater than 100 miles. 13 have diameters greater than 31 miles. This far exceeds what you might find around Jupiter. Jupiter has 4 large moons, those moons that were discovered by Galileo, the Galilean moons. But the moons of Saturn are really unique. And of course, Saturn has the second largest moon in the solar system, Titan, which is especially unique because it's the only moon in the solar system with an atmosphere. Here's a view. We can see the relative sizes of the moons. What's kind of interesting too is that there are moons which kind of co-orbit. They either share orbits or they're they're part of a much larger moon, which is orbiting plus or minus 60 degrees from around that larger moon. Unfortunately, we'll not be able to show all of those because we have a limited amount of time, but we're going to look at some of the more interesting moons. And of course, Saturn has rings, which are very prominent. The innermost ring is labeled the D ring. We have the C ring, then the B ring, which is the brightest ring. The gap between the B and A ring called the Cassini Division. Outside the A ring, we have a smaller ring called the F ring, which is kind of unique. A little bit further away, we have the G ring, and then we have the E ring. And we actually know what's producing the E ring. And we'll talk about that a little bit when we go talk about the individual satellites of Saturn in more detail. So we're going to start off actually by talking about the F ring and a couple of moons that orbit very close to the F ring, Prometheus and Pandora. You can see the image here. Prometheus is a small moon which orbits inside the F ring. Pandora is a small moon which orbits outside the F ring. And from this image, you can also see that the F ring is not one ring, it's actually a series of rings. And like all the other rings of Saturn, they're really composed of individual chunks of ice particles that vary in size anywhere from the size of a speck of dust up to large boulder size, perhaps maybe on the order of a school bus size. We don't really know what those individual chunks look like because the Cassini spacecraft never got close enough to the rings to see that. But all of those chunks are orbiting around Saturn. So both Prometheus and Pandora are roughly the same size. Here's a close-up of Prometheus, and you can see that it's getting close to the F ring, and you can see that it's actually interacting with the F ring. And in this view, you can actually see it interacting even more. Here's a series of images which show the interaction of the Prometheus moon with the F ring. Now, Prometheus has a slightly elliptical orbit, and so every once in its orbit, it tends to be a little bit closer to the F ring. When it's closer to the F ring, what it does is its gravity will pull some of the icy chunks out of the F ring and create that little pattern that you see there. Prometheus orbits its orbit is about 14.7 hours around Saturn, and because it's closer into Saturn, it orbits a little bit faster than the material that's in the F ring. So every time it goes close to the F ring, it's actually at a different position on the F ring, about 3.2 degrees different. And so you can actually see a series of these streamers that have been pulled out of the F ring by Prometheus. Here's a view of what Prometheus looks like. Again, it's not a small moon. It's kind of has an irregular shape. About 63 miles along is the average diameter. Outside the F ring is Pandora, and you can see that little dot on top there, that's Pandora. Both Prometheus and Pandora are a type of moon called a shepherd moon. And they're called that because what they do is they help to kind of maintain the F ring so that the F ring doesn't actually either get larger or smaller. They kind of maintain its size. Here's a close-up of Pandora. It's a little bit smaller than Prometheus. You can see it's heavily cratered. But if you look, it's kind of interesting. It seems like the craters tend to be filled, and they're probably filled from some ice chunks from the ring itself that got pulled in by the gravity of Pandora. Now we're going to go a little bit farther out. We're going to go to the moon Mimas. Mimas is shown here. It's larger than either Prometheus or Pandora. It has a diameter of about 247 miles. And scientists kind of think that the amount of material that are in the rings of Saturn is roughly about a few times the mass of the moon Mimas. And Mimas is not a very big moon. So that means that the amount of material that are in the rings is not really that much, even though it looks pretty massive because the rings extend for hundreds of thousands of miles around Saturn. The most prominent feature on Mimas is the Herschel crater, which is shown here. So you can see that Herschel crater, you can see a prominent central peak due to the crater. It's about 80 miles in diameter. Then it's thought that whatever impacted it, probably billions of years ago, when the solar system was first forming, it was almost large enough to break Mimas into two. It didn't do that, but it was a very large collision. One of the interesting things about Mimas is the surface temperature. Over here on the left, you can see the expected surface temperature where the sun is shining on it. It's going to be the hottest right in the center and cooling off as we go away from where the sun is shining. The actual temperature distribution measured by the Cassini spacecraft is shown on the right. It looks like a Pac-Man. And what's thought is that that surface has a very high thermal conductivity, and so it's basically able to carry the heat away very rapidly. Why it has this strange shape like this is totally unknown. So that's another interesting thing for the scientists to be able to study for years to come. Well, Mimas is one of the large satellites of Saturn. Another large satellite of Saturn is Enceladus, and there's a picture of it. Most of the moons of Saturn are, their outer surface is ice covered, and you can see in this view, it's very bright, ice covered. We're looking at a view towards the south pole of Enceladus. And the interesting thing here is that near the south pole, the number of craters is very much reduced, almost zero in some cases. Enceladus actually orbits within the E-ring, and there's a reason for that, which we'll see in a bit. The north pole of Enceladus is shown in this view, is much different than the southern pole. It's heavily cratered. When the scientists see a surface that's heavily cratered, that indicates to them that the surface is fairly old because the cratering is thought to have occurred in the early part of the formation of the solar system when there were a lot of rocks and debris that was floating around, crashing into the planets and the moons. And so you can see there are craters within craters in this view as well. Here's a false color image of Enceladus where some aspects of it are kind of highlighted. We're looking basically towards the South Pole. And down here in the bottom, you can see a series of parallel lines. These stripes, sometimes they're called tiger stripes, are very important because something really unique kind of happens on them. Here's another picture where we can kind of see, again, near the South Pole, some different fractures and folds. You can see what's called a Y-shaped discontinuity over there due to some of the fractures that are occurring. Scientists, because Cassini had so many different types of instruments, they were able to measure the heat coming off the surface using the infrared spectrometer on the Cassini spacecraft. And they measured the heat flow at the south polar region of Enceladus and found it to be about 6 gigawatts. That's a huge amount. It's equivalent to about a dozen electric power plants. And scientists were really unsure what's causing that. We don't really know at this point what the heat source is, but it appears to be closer to the south pole of Enceladus, not really centered on it. Tidal movement could be one thing due to the gravitational pull of Saturn as Enceladus orbits around there. That certainly is one aspect of it, but there may be other reasons for that heat source as well, which are not exactly known at this time. Well, what's kind of interesting about Enceladus is because at that south polar region where we have those multiple fractures, we have geysers. Here's a view of some of those ice geysers erupting from near the south polar region of Enceladus. Here we see another view of this, and you can actually, there are about 30 separate jets of different sizes that can be seen in this image. The Cassini spacecraft was able to fly through the erupting geysers and analyze the composition of the gases that were coming out as well as the ice particles. And the spacecraft found that about 98% of the gas in the plume was water, about 1% hydrogen, and the rest is a mixture of other molecules, which include carbon dioxide, methane, and ammonia. In the solid particles, they detected salts and carbonates. There was a paper in Science about 3 years ago in 2017 that indicated that molecular hydrogen was also found. And in fact, enough molecular hydrogen was found in those the gases erupting from those geysers. It could sustain microbial life. And here's a picture of Enceladus, which is kind of shown here in the center, orbiting in the E-ring. Enceladus orbits basically in the middle of the E-ring, and in fact, Enceladus is the cause of the E-ring. Those erupting geysers, some of the ice particles have enough velocity to escape the gravitational pull of Enceladus, and they go into orbit around Saturn, forming the E-ring. Those particles that don't have enough energy to escape the gravitational pull of Enceladus fall back on the surface, fill up any craters, and that's why near the south polar region of Enceladus, there's very few craters, if any, because they've all been filled up by the infalling ice particles from the erupting geysers. Scientists are trying to model what may be occurring, and what's thought to be occurring right now is that there's some solid surface, which is probably providing the heat source. Above that is an ocean of liquid water. And above that ocean of liquid water is an icy crust, which has fractures. And it's through these fractures that the erupting geysers occur. So there's a lot more interesting information which scientists are going to be analyzing for many years to come for Enceladus. Well, we can continue on. We can look at another moon of Saturn, and we can look at Rhea. Rhea is the second largest moon of Saturn. It has a diameter of about 950 miles. You can see the surface is fairly bright because the surface is mainly covered with ice, but it's also heavily cratered, implying that the surface of Rhea is very old. But what's kind of unique about surface is the craters. As you can see in this image, if you look at some of the craters, they have polygonal rims. Most craters that we see are fairly circular in shape. But some of the craters on Rhea have are polygonal, and so that may imply something about the composition of the surface of Rhea itself. Here's another view. You can see a close-up of the craters and the polygonal nature of those rims as well. And again, this heavily cratered surface indicates that the surface of Rhea is very old. It probably hasn't changed for billions of years. If we kind of continue onward past Rhea, we encounter the largest moon of Saturn, which is Titan, which is shown here. Titan is unique in the solar system because it's the only moon with an atmosphere, or really a substantial atmosphere. Some other moons have atmospheres that are not substantial, very thin. But Titan's atmosphere is thick. It's about 1.5 times denser than Earth's atmosphere. It's composed mainly of nitrogen and methane, 95% nitrogen, 5% methane, plus traces of other hydrocarbons and hydrogen cyanide. Its orbital period, it takes about 16 days for Titan to orbit around Saturn. It's a fairly large moon, again, the second largest moon in the solar system. It's about 40% of the diameter of the Earth, much larger than Earth's moon. But what's unique about Titan, besides the fact that we can't see the surface, is the surface temperature is about minus 178 degrees Celsius, minus 288 Fahrenheit. And at that temperature, methane, natural gas on Earth, what we use to heat our homes, boils and or is a liquid. It doesn't boil, so it can exist as a liquid on the surface of Titan. And in fact, ethane can also exist as a liquid on the surface of Titan. And here we can see some of the haze layers, the outer haze layer on Titan as well. So we can't really see the surface directly. And in order to see the surface, the Cassini spacecraft uses radar probe to basically image the surface. We'll see some images of that in a bit. But what's occurring in the atmosphere of Titan is basically a whole series of chemical reactions. The nitrogen and methane in the atmosphere are using sunlight and energetic particles as an energy source. They're combining into very large organic molecules, that is, molecules containing carbon. These molecules become very large, and in fact, they form a solid material called a tholin. Tholin is a Greek word, which means hazy or muddy. It was coined by Carl Sagan and Vishnu Kher in a paper in Nature in 1979 entitled Tholins, Organic Chemistry of Interstellar Grains and Gas. What's unique about tholins is that they're organic solids produced from the irradiation of ices or gases such as methane, nitrogen, water, ammonia, carbon monoxide, as well as others. And tholins turn out to be very incredibly chemically complex. At Johns Hopkins University, Sarah Horse actually made tholins in the laboratory and analyzed them and found that they contain at a minimum 10,000 different molecular formulas. And in fact, they've detected molecules in tholins with masses equivalent to about 80 carbon atoms, although they think that they're even larger in the atmosphere of Titan. So basically, these chemical reactions begin occurring in the outer atmosphere of Titan. They produce these tholins, which get larger and larger. Eventually, they will land on the surface. But that is what is producing that haze that we cannot see through. That was the reason why the Cassini spacecraft had the Huygens lander. It was designed by the European Space Agency, and about 6 months or so after Cassini went into orbit, it detached itself from Cassini and took about 2 weeks to get to Titan. When it got to Titan, then it entered the atmosphere and used parachutes to slowly descend through the surface of Titan. And as it did that, it analyzed the composition of the atmosphere, took images of the surface itself. And we'll look at some of that here. The image that you see on the right that was taken from an altitude of about 8 kilometers, roughly 5 miles or so, shows probably some land surface, but here it looks like something like a shoreline. We'll talk about that in a minute. Here is a view after landing on the surface. The Huygens probe was able to survive, about an hour or so on the surface of Titan before the cold got to it. And here's an image that is sent back. You can see everything appears to be reddish. That's due to light scattering, due to the tholins that make up that atmosphere, those small particles. And we see some rocks over here, which are really chunks of ice. You know, this one is probably roughly this size or so. So the surface of Titan is, again, probably composed of water ice, but also it has a lot of tholins, which actually came from the atmosphere, which have landed on the surface. Now, on the image on the right, we see something which looks like a shoreline, and that it's turned out probably is what it is, because the Cassini spacecraft has found lakes on Titan, mainly in the northern hemisphere. Here's a picture of one. Here's a lake with an island within the lake itself. This island is about 62 miles by 93 miles, roughly the same size as the big island of Hawaii. But the liquid itself that makes up this lake is unique because it's now water. Water can't exist as a liquid on Titan. It's too cold. That liquid is liquid methane, or actually a combination of liquid methane and ethane. Here's another view of a lake, the second largest known body of liquid on Titan, bigger than Lake Superior. This lake has an average depth of about 160 feet with a maximum depth probably greater than 650 feet. So there's a lot of liquid methane and ethane, which has filled up that lake. Here's an artist's view of a lake on Titan. And new research using radar data from Cassini plus modeling has proposed that the lake basins are really explosion craters, which could have formed when liquid molecular nitrogen, which makes up the bulk of the atmosphere of Titan, these deposits within the crust warmed quickly for some reason, and they quickly turned to vapor, blowing holes in the moon's crust. And so it would make these depressions, which eventually got filled up with liquid methane and ethane. And there's also evidence that we have rain that occurs on Titan itself. And that, of course, that rain consists of liquid methane and ethane. So scientists think now this is the proposed model for what Titan is composed of. We have an organic rich atmosphere. And then we have the surface is really a decoupled icy shell. And then beneath that surface is a global subsurface ocean. We don't know the depth of that ocean, but we know it's probably composed of liquid water. Below that is some high pressure ice and then a silicate core. And the reason we think that there's a subsurface ocean on Titan is because of some measurements that Cassini has made. If there was no subsurface ocean, the Cassini spacecraft would basically look at the elevation or the height of different land areas on Titan using its radar imager, and it would look at the solid tides that were produced by the gravitational pull of Saturn as Titan orbit around Saturn in its orbit, which is, of course, is not entirely circular, slightly elliptical. And so these solid tides on the surface, if there were no liquid ocean, would be very small, about 3 feet in height. But what the Cassini spacecraft found is that those solid tides are approximately 30 feet as high, 10 times as large. And so this implies that there's probably some liquid water or something which decouples the surface from the rest of Titan themselves. So a lot of interesting science going on in Titan. Here's the last view of Titan, just a few days before the end of the Cassini mission. And again, you can't see the surface because of that haze from all of the Tholins. But scientists are analyzing the data. They're finding a lot of interesting things about that, and they'll be doing that for years to come. Now let's take a look at Saturn itself. One of the unique features of Saturn is at the North Polar region, this sort of hexagon-shaped area is a jet stream. And that black spot is really the North Pole of that. You can see all these different layers. They represent the different bands on the outer atmosphere side of Saturn, just like Jupiter. These bands have winds which are going sometimes in opposite directions. They can go at very high velocities as well. That hexagon, that jet stream area that we see in the North Pole, it's kind of interesting because it changes color. In November 2012, the top image shows you is sort of bluish. Down here in September 2016, it was more of a golden color, and that's due to photochemical haze produced in the atmosphere because at this point, the sun was shining more in the northern hemisphere of Saturn than in the above image. And here's a view of looking at it from two different times. Again, in 2013, more bluish, and 2017, it's a totally different color due to some of that haze, photochemical haze produced by the sunlight. And here's an interesting view. This was looking sort of a close-up of the outer atmosphere of Saturn in the infrared. I put it in there because just to show you the really chaotic nature of those bands. You know, they from far away, when you image them, they look kind of, nice and sort of parallel, but there's a lot of turbulence that's occurring in the atmosphere. And in this infrared image, the different colors represent different wavelengths of light. And so we can actually see in great detail the turbulent nature of the atmosphere of Saturn. And of course, the most prominent feature are the rings of Saturn, which are shown here. The innermost ring is called the D ring, then the C ring, then we have the B ring, which tends to be the brightest. The Cassini division is the gap between the B and A ring. Then we have the F ring, the G ring, and the E ring, of course, is due to the moon Enceladus. What's kind of interesting is if you look at the rings, there is a term called the Roche limit. This is the minimum distance at which a large satellite can approach a primary body without being torn apart by tidal forces. For Saturn, the Roche limit is about 91,300 miles. The F ring, which is shown here, is at 87,100 miles. So what scientists think is that the rings themselves are relatively new, and they're probably the result of a moon, which probably got too close into Saturn and was broken apart by the gravitational pull of Saturn once it got within the Roche limit. Now, the rings extend for hundreds of thousands of miles, but they're very thin. Here's a nice view taken back by Cassini in 2005, an edge-on view of the rings. And you can see that the rings are very thin. They're only, tens of meters thick, composed of all those ice particles that make them up, orbiting around Saturn's equator. So even though they have a large extent, the rings themselves are very thin. Different rings, though, their thickness is a little bit different, and that has something to do with the different types of icy particles that may persist within them. This is from a paper taken in Science magazine in 2010, where they were looking basically at the optical depth through the rings themselves. So if you maybe look at a star, you watch as the star pass through the different parts of the rings, and you can get an idea of how thick the rings are. So you can see the C ring, which is shown here, seems to be very thin. The B ring, the brightest one, is very thick, lots of particles which block the light going through them. And we have the Cassini division. You can see it's not entirely empty. And then the A ring, which extends past the Cassini division. So the ring particles, when they orbit around Saturn, depending on their distance from Saturn, they're orbiting at different speeds, but relative to each other, they have a very small difference in velocity on the order of maybe 0.01 to 0.1 centimeters per second, not a lot. And so when they do collide, instead of necessarily breaking apart, they may combine together to make bigger chunks of particles. That looks maybe to be more prominent in some rings than in other rings. Here's a close-up of the Cassini division, which is the gap between the D and the A ring. And you can see the gap, it's not empty. There's still ring particles in there. That gap is fairly wide. It's almost 3,000 miles in width. And it's thought to be caused by the moon Mimas, kind of a resonant effect. It turns out that the particles in the Cassini division orbit Saturn almost exactly twice for every time that Mimas orbits. And that builds up gravitational nudges from the moon, enough to remove a lot of the material from the Cassini division, not all of it, but enough to reduce the size and make it look like it's relatively empty, even though there are some ring particles which exist in there. And so when you look down really in a lot of detail at the rings, you can see a lot of interesting features. One of them is things called propellers, which is shown here. We're looking at the same propeller from the top and bottom view, taken by the Cassini spacecraft. But it's thought that these propellers are right in the center is a small moon, which we can't image. It's too small to see, but it's bigger than the surrounding ring particles, and it's orbiting. Its gravity is basically perturbing some of that ring particles, producing that propeller-like effect that we see here. And if we look at a view of the rings, you can kind of see the rings themselves, and you can see, you know, that they're really composed of multiple rings, all the different particles that are in orbit around Saturn itself. It's thought that the rings are relatively new. The findings from the Cassini spacecraft indicate that the rings formed between 10 million and 100 million years ago. One of the reasons we think they're new is because they're very bright. They haven't had time to accumulate some darker debris that some of the other moons have accumulated as they get older. And again, they're not very massive. They're probably due to the breakup of a relatively small moon if it got in too close to the gravitational field of Saturn itself. And here's one of the last views of the rings. The last 20 orbits or so of the Cassini spacecraft were actually inside the rings. So it was actually its closest point into Saturn was between the D ring and Saturn itself. And so it was able to image the rings from a different location than before. Before it was well outside the rings to avoid any collisions. But near the end of its mission, scientists decided that they wanted a closer view of Saturn and also a different view of the rings as well. Here's a nice view of the atmosphere of Saturn where you can see haze on the horizon, and then you can see an image of the rings right above that. And here's a view of the impact site, kind of a black and white view, and here's a color view of that impact site. This is the final image that was sent back by the Cassini spacecraft, sent back on September 14, 2017. The next day, it actually entered the atmosphere of Titan, of Cassini, destroying the spacecraft itself. There's a lot of science that emerged from that, a lot of things that scientists didn't know. Just to kind of summarize, complex organic compounds embedded in water nanograins rain down from Saturn's rings into its upper atmosphere. Scientists saw water and silicates, but they were also surprised to see methane, ammonia, carbon monoxide, nitrogen, and carbon dioxide as well. The composition of the organics that was found is different than that found on the moon Enceladus and different than that found on Titan. So it looks like there's really three distinct sources of organic molecules in the Saturn system. And Cassini saw how the ring molecules interact with the planet and how they fall directly into the atmosphere themselves. Unlike every other planet in the solar system, Saturn has a magnetic field which is almost perfectly aligned with this rotation axis. The difference is less than 0.0095 degrees. For example, Earth's magnetic North Pole is off about 11 degrees from the spin axis North Pole. From everything that scientists know about how planetary magnetic fields are created, Saturn should not have one, but it does. Very strong ring system. So the Cassini spacecraft sent back a rich detail of images and scientific data from Saturn. It turns out that it entered because it was running low on fuel and scientists were not able to control it, and because at least two of the planets have what scientists believe to be an ocean of liquid water beneath the surface, scientists did not want the Cassini spacecraft to crash on any of those moons and potentially contaminate them. And so what they did was they directed the Saturn spacecraft to enter the atmosphere of Saturn. And it did that on the morning of September 15, 2017, and it was burnt up and destroyed, but it also prevented any contamination from occurring. And here's a view of all of the different orbits from 2004 through 2017. They're all color-coded for different missions. The green ones close in are the last set of orbits that got really close into Saturn, inside, in fact, in between the rings and Saturn themselves. And the very last image I want to show you is an interesting one. This is a view of Saturn taken from behind Saturn, an image that we can't see from the Earth. You can see the shadow of Saturn on its rings. This was a series of 36 images that were merged together to give this view. So this shows you a nice view of Saturn. What I've given you is really sort of a very broad overview of the Cassini mission itself. And I hope it gives you some idea. You can go to NASA's websites and look at it in more detail as well. Thank you for listening.